Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1207. Let's just jump into it. There seems to be the video here. Oh, yeah, there it goes. It wasn't visible before. All right. Okay, I think we're good. Let's actually jump into it. So the bulk of the plan for today is to teach you one more integration technique and then sort of go over integration and kind of talk more about this art of integration that we've been talking about, like how to approach integrals, what to look for, when to look for it, and that sort of thing. We already know the first three steps, which are always the same, always in that order. But we do need a little bit more nuance for when the other techniques might be of use. But let's talk about what we did last time. So last time we talked about partial fraction decomposition. We learned how to do partial fraction decomposition. We also learned about this method called the cover-up method, which is very useful when the denominator factors that you're looking at are either non-repeating linear factors or the highest power of a repeating linear factor. You can actually find those values by covering up the denominator and plugging in a number that would make the expression 0, covering up the denominator of the original expression, that factor, and plug in the number that would make that denominator 0, and that would actually be the coefficient, which is very interesting and very weird. But it works and it's quick, and I gave you some sort of algebraic reason why this would work, but it's also just generally one of the applications of the residue theorem. So we did essentially last class, we spent a lot of time on partial fractions because a lot of it also takes a lot of skills that we needed and probably forgot it from pre-calculus and all that stuff, like how to factor things, which we looked at using the rational roots theorem in our final example, and just dealing with rational expressions, as well as just knowing now how to break down one big fraction into a lot of smaller fractions. So we did some examples. We looked at the methods for how to find the arbitrary constants that showed up, and that was pretty much it. We spent a long time talking about that, as well as using substitution to help us out some of the time. And yeah, but the idea is here that partial fractions, as you can see from the examples we were looking at, they're very useful when we have integrals that are either integrating rational functions, so just a ratio of polynomials in which the denominator is factorable and the numerator is of a lower degree than the denominator, or via a substitution, you can make that the case. So for example, in example E, it is currently not the case that that is a rational function, but by doing a substitution in example E, we transformed it into a rational function. So something doesn't have to look like a rational function in the beginning. If after some substitution, you can get it to look that way, and the denominator factors and the numerators of lower degree, you can use partial fractions. And generally speaking, as a rule of thumb, I would say, if you're in a situation where you can use both partial fractions and a trig sub, I'd probably err on the side of doing the partial fractions, especially since if it is the case that you can use both, chances are that's going to be like an a squared minus x squared or an x squared minus a squared case, which means it's going to factor into linear factors, right? And so that would be nice. That's usually going to be the case. I mean, sometimes it might not be, but it kind of hints to you that it's going to be a situation where it'll be easier to do it with partial fractions, and chances are you'd also be able to use the cover-up method, at least with the problems that you'll typically see in a Calc 2 class. So that was pretty much it. So I do want to talk a little bit about trig sub again, though, because there's something that I want you to notice in trig sub. So in trig sub, we had these expressions, right? They didn't have to be rational expressions. But the idea is, notice one thing that's in common with all these integrals that we use trig sub on. And one thing that might stand out to you is that there are no trig functions originally, right? So if there's an integral that you want to use trig substitution on, it wouldn't be a trig integral in the first place. It's some sort of other integral that we introduce trig functions to simplify the process, right? So we encounter an integral that has no trig in it, but because it has a very nice expression where we can take advantage of trig identities, we introduce trig into the problem to make it more doable. And so a question that someone might ask or think is, could we possibly do the opposite? Are there situations in which I can see an integral and it's actually a trig integral, but it's very difficult to use the techniques that we learned in the section 7.2? Would it be possible to get rid of trig, kind of do like this inverse trig substitution and get rid of all the trig and maybe get something nicer that we can do without the trig? And the answer is yes. And that is what that leads us to our lesson today, which I actually typed up some notes for you. So such a thing is called a Weierstrass substitution. It's named after a mathematician by the name of Weierstrass. And it's essentially like an inverse trig substitution, or sometimes we call it an inverse tangent substitution. And that's because it uses specifically the inverse tangent. So it turns out by doing this, you can actually undo trig functions from an integral and turn it into something without trig. And actually do it easier. So when this applies is when your function looks like essentially a rational function with trig in it. That's when it would be very nice. So essentially after you replace all the trig, it would actually look like a function that is a ratio of polynomials, but a more generalized polynomials like x's and y's. So something like this 1 over x plus y plus 1, that is a rational function in terms of x and y. But imagine if the x and y were replaced by trig functions, like I replaced the x with sine x and the y with cosine x. So that's sort of like a rational trig function. So it kind of looks like a rational function, a ratio of polynomials, but it has trig functions instead of the regular variables. And it turns out whenever you see an integral like that, one option that for attacking such an integral would be something like a Weierstrass substitution, where you would kind of go like from something like this to looking something like this, but in a single variable, of course, because we're in Calc 2. So here's how the substitution actually works. Given an integral where f is a rational trig function, which means it looks kind of like a ratio of polynomials, but instead of x, you see trig functions in places of where the variables are. Then you can actually do this substitution. It's with a t, which is traditional. T equals tangent x over 2. Now, if you were to solve for x, you would know that x would be an inverse tangent. And it turns out that this guy will enable us to rewrite an integral in terms of non-trig functions. And it's really interesting how that happens. So I just want us to break down how that happens. But this is the main thing right here. This is the substitution that makes it happen. So this is also something that we've been talking about, how sometimes your substitution doesn't just have to be u equals something. Like you can kind of get almost anything to work as a substitution, provided it's convenient enough. And the ones that become the main methods are the ones that are useful across a wide range of problems. And it turns out this sort of tangent substitution is useful across a wide range of problems. And it can allow us to simplify a lot of trig integrals. So let's actually talk about that. So let's assume that we make this substitution. And at the moment, you might not see why that would be useful, but in me working stuff out, you're going to notice why it's useful. But let's actually figure out how to actually do the substitution, right? So we know we have an integral f of x dx. When you're doing a substitution, you're going to need to replace the dx part. You're also going to need to replace the function part. So let's actually talk about what happens to the dx, right? So if we let t equals tangent x over 2, this of course would mean that if I take tan inverse of t, that gives me x over 2, which of course would mean that your x is equal to 2 tan inverse of t, which means that your dx would be, you differentiate that, which we know what the derivative of tan inverse is now. So that is an important equation to know. Right? So once you do this substitution, your dx will always be this expression, right? Always. So you can just know dx becomes this once I do a Weierstrass substitution, right? And the Weierstrass substitution is this guy. Okay. So doing that substitution, my dx will transform into this expression, 2 divided by 1 plus t squared times dt. Okay, now let's talk about what happens to each trig function that appears, right? So we're assuming our f of x has a bunch of trig functions in it, right? So sines and cosines and all that stuff. So under this substitution, what actually happens to these trig functions? Well, if you have t equals tangent x over 2, okay, that essentially would mean that you can actually set up a triangle here with the angle x over 2. So here's the angle x over 2. And here I can think about this as t over 1. I know tangent is opposite over adjacent. So that means this is opposite, this is adjacent. And then I can use Pythagoras theorem. That's going to mean that this side is going to be 1 plus t squared. Okay. Now, this, of course, would also mean from this triangle, maybe I'll put it under the triangle, that sine of x over 2, right, is going to be opposite over hypotenuse. And it also means that cosine of x over 2 is equal to adjacent over hypotenuse. Okay. So that's actually sine and cosine of the half angles. And so we might not want to know what happens to the half angles. We want to know what happens to the sine of the original angle. So what would this mean for, say, something like sine of x? Well, what I can notice is that this is actually just sine of 2 times x over 2. And then what we can do is we can actually apply the double angle formula for sine. So this is actually going to be 2 sine x over 2 cosine x over 2. Here I'm using the double angle formula, or it's called the, double angle formula for sine. We know that sine of 2x is equal to 2 sine x cosine x. And I know what sine x over 2 and cosine x over 2 is. It's right above there, right here. So what I'm going to do is I'm just going to multiply those guys together and then multiply by 2. And so that means whenever I see sine x in an integral, I can actually replace it by 2t divided by 1 plus t squared. Right? So under this substitution, a sine function is equivalent to this rational function, 2t divided by 1 plus t squared. Similarly, I can do this for the cosine. So if I see cosine of x, I can have, this is the same as cosine of 2 times x over 2. So I can apply the double angle formula for cosine. So that is going to be cosine squared x over 2 minus sine squared. x over 2. And this is from the double angle formula for cosine. So that's actually, that says cosine of 2x is equal to cosine squared x minus sine squared x. There are a bunch of ways to actually write this one. It's also 2 cosine squared minus 1. It's also 1 minus 2 sine squared. Right, but those are all double angle formulas that you learned from pre-calc. So what you can do then is you can square the cosine and then subtract that from the square of the sine and subtract the square of the sine. So if I square the sine, I get t squared over 1 plus t squared. If I square the cosine, I get 1 over 1 plus t squared, and then I subtract them, and that essentially just gives me the final thing that we want. It's 1 minus t squared over 1 plus t squared. And so that ends up being an expression that creates your cosine that you can replace cosine with. So the upshot is, if I have a trig integral and I apply this substitution, I can immediately replace my dx with this. And everywhere I see a sine function, I can replace with this. And everywhere I see a cosine function, I can replace with that. And you notice that these are all rational functions. I went from a situation where I had trig functions to a situation where I have none. So that's actually pretty nice. And we can summarize these guys in this table right here. Okay, so that kind of summarizes what I mentioned. So under the Weierstrass substitution, which is t equals tangent x over 2, with that substitution, your dx becomes 2 over 1 plus t squared dt. Your sine of x will become 2t over 1 plus t squared. Your cosine of x would be 1 minus t squared over 1 plus t squared. Of course, your tangent x is just the sine divided by cosine. So that just becomes 2t divided by 1 minus t squared. And your cosecant, secant, and cotangent are just the reciprocals of these guys respectively, right? And so your integral that originally had trig functions in it, provided they were a rational trig function, by making the substitution, you'll often get into a situation that's a lot nicer. And you can use techniques other than the trig techniques to do it. So let me show you a simple example to show how this would work. So let's say I have an equation like this. So this is an integral of a rational trig function, right? So if my sine of x was just another variable, like say just x, that would be a rational function. So that's what we call a rational trig function. If I replace all my trig functions with just variables, it would look like a ratio of polynomials, right? In that situation, we can apply a Weierstrass substitution. So here's what would happen with this guy. Apply Weierstrass. So this means your t equals tangent x over 2. By the way, that's going to help us when in our back substitution. Maybe I should mention that. Okay, so I apply this. Now what's going to happen? We know that our dx is going to become 2 over 1 plus t squared dt. And we also know that our sine of x is going to become 2t over 1 plus t squared. Okay, so I know that these two things will happen. These two things would be true once I do this. And so I can actually plug this in. And so if I call this I, this will be the integral of 1 . This will actually be the integral of 1 divided by 1 plus sine, which is 2t over 1 plus t squared, times dx, which is going to be 2 over 1 plus t squared dt. Now what I'm going to do is I'm going to simplify this so I can take this 1 plus t squared, and then I'm going to multiply out the denominator. So this is going to become the integral of 2 divided by 1 plus t squared plus 2t. Now, of course, that's just t squared plus 2t plus 1. That actually factors. And that's something that after an easy substitution like u equals t plus 1, you want to integrate 1 over u squared. That's just the power rule. So that would actually just be minus 2t plus 1 to the minus 1. So let's substitute. Now we want a back substitution because our original function was in terms of x's. So we can't give an answer in terms of t, but we know that our t is just tangent of x over 2. So everywhere I see t, I'm just going to go in now and put in tangent x over 2. And that's our answer. Okay. So you have this trig integral. And after doing the Weierstrass substitution, I get a non-trig integral. And it's actually a pretty easy non-trig integral. So that's an example. Any questions on this method or anything that we've done? That's essentially the method. That's the Weierstrass substitution. It's just another substitution technique. And aside from that, right now, it's just a matter of doing examples to get used to it. There's really nothing else for me to show you at this point. It's just a matter of doing the substitution, replacing all your trig functions based on these equations, and then dealing with the integral afterwards, which we know a lot of ways of dealing with rational integrals at this point. So, yeah, questions on this? Okay, so got the thumbs up from Nadia, or was that from earlier? That was probably from earlier. But yeah, so hopefully that's. I have a question for you guys though, because I see here in parentheses, also another way. So think of this as my challenge to you guys. Could you have done this another way? Like, let's pretend like I didn't tell you about the Weierstrass substitution, but you saw this on an exam. Like, what would you have done? How would you have gotten your way out of this? Give me some ideas. Any ideas? Do this another way. Okay, I'll give you a hint and maybe we can finish it off. And it might also suggest to you how to deal with things if you're in a similar situation. I'm going to multiply and divide by something. Let's say I told you that a nice way to do it was to just multiply and divide by 1 minus sine x. Okay. So that's the hint. Anyone see how to proceed? Like if I gave you that hint, like what would happen here and how would you deal with it? Don't be shy. Remember, we have a test in like a week, so you should try to okay. So someone mentioned that they thought they would use partial fractions. But if that's not the case, they're out of ideas, which is okay. All right, so let's talk about that first. Why is it the case that partial fractions would not work here? Can anyone tell me why partial fractions wouldn't be something we can try? Right, it's not a rational function. It's not a ratio of polynomials. The moment there's a trig function in it, partial fractions can't work. Not unless you do a substitution to get rid of them, right? So there was an example yesterday that we did with some trig functions in it. But notice that before we could apply, yeah, example D. Before we could apply partial fractions, though, we actually had to get rid of the trig functions. A, B, C, D. A, B, C, D. Yeah, so this guy, we started out with trig functions, but notice that we did a substitution and transformed it into a rational function. So partial fractions only works when you have rational functions, meaning ratio of polynomials. And so if you have a trig function, if you want to use partial fractions, that means you can just use a substitution to turn it into a polynomial like that. But of course, here that would not work, because if you do something like u equals sine, you don't have a cosine to get the substitution to work. So yeah, partial fractions wouldn't be an issue, but maybe something else. So maybe after this hint, what would happen after this hint? How does that help? What does that get us?
I think we could use the secant squared identity on the denominator.
Okay, how would that work?
When you multiply it out, you get 1 minus sine squared x.
In the denominator?
Yeah.
1 minus sine squared, right? Because difference of squares. Right, we have 1 plus something times 1 minus something, right? A plus b times a minus b, get difference of squares. And in the top, it'll just be 1 minus sine x. All right. And what happens now?
I think I'm actually not sure whether it's positive or negative secant squared x. I'd have to check the exact identity, but.
Well, 1 minus sine squared? What is
Yeah,
that equal to?
I don't remember the I don't remember if it was 1 minus sine squared or sine squared minus 1. I think it's
for
equal
what?
to secant squared x.
No, I think you're thinking of a different Pythagorean identity. You want the original
Oh.
one. Right, remember sine squared plus cosine squared is 1. So 1 minus sine squared is actually cosine squared. Right, the identity with secant, it's 1 plus tangent squared equals secant squared. Or you can write it as secant squared minus 1 is equal to tangent squared, something like that. But here we have this. What would you do at this point? Ideas? What would the next step be? Remember, you'd go in your head, is this a basic rule? No. Can I simplify this to be a basic rule? Any simplifications you think might help? So we don't see that, you might go ahead and think maybe a substitution. If you were to do a substitution, what would be the thing you'd want to substitute? How would you be able to apply that sort of thing? It's kind of where you should be thinking. Any ideas? No ideas? You see this, you just give up? Give up on life? Just put hand in your paper and just walk out the door. And go like, I don't know, travel the world, backpack through Europe, you know. Open up a farm. The lemonade stand. I saw this article the other day about this little 11-year-old girl who opened up a lemonade stand and became like a millionaire. I don't know what was in her lemonade, but it's just, that's what you're gonna be like, man, I'm gonna open up a lemonade stand. It'll be easier. Okay, come on. Give me a guess. Doesn't matter how good it is. I just want to know what you guys are thinking. And I don't mean to know the answer. Like, I just mean the next step. Like, at this point, what is the next thing you do? Don't even worry about if it's going to work out. I just want to know what you're thinking about. So someone mentioned to me trig sub. Trig sub would not work because there are already trig functions. Right, because trig sub, remember, I just point out the thing with trig sub is there are no trig subs in the beginning. Right, there are no trig functions in the beginning. Right, this is a trig integral, so a trig sub wouldn't work. Okay, if you want to do a u sub, what would you substitute? Yeah, take a guess. What would you substitute? What would make sense to substitute with a u sub? Well, it can't be both. It has to be one of them. I mean, there'd only be two options, right? The sine and the cosine. Okay, so if you say u equals sine, what would the du be? Right, cosine x dx. And do you have that? Do you have a cosine x in the numerator? Oh, by the way, just so you guys don't think I'm crazy, like someone is actually direct messaging me in the chat, so I'm not talking to myself. I just realized no one else would be seeing the conversation. Yeah, so someone is messaging me in the chat with some suggestions, and I'm trying to figure out like where we want to go. Okay, so you want to do a substitution. So you have a couple options. Either the sine or the cosine is going to be a substitution, right? Now, you said u equals sine. Now, what would happen if you let u equals sine? Your du would be cosine. And the question is, do you have cosine x dx in your integral? You don't have a cosine x dx, right? The cosine is at the bottom, right? So you can't use that. So if you decide that you want to use a substitution, u equals cosine would make more sense because your du would be the negative sine x dx. And sine x dx, you kind of have that right here. The problem is this one in the front is going to mess that up because you don't have sine x dx, you have 1 minus sine x times dx. So this part here works out well with the substitution, but that part does not. Right? Like when you're making a substitution, you have to see, do I have something that makes that substitution useful? Like would my du be somewhere in the integral that I can make sense of? So here, the one is kind of messing things up for us in terms of a substitution. If you want to do a substitution, u equals cosine would make sense, but the I have another suggestion here. So I think you meant u equals cos. Okay. So there's an issue with the last thing you said. Like if, yeah, still an issue. So again, let's say we only had the sine x over the cosine squared, right? So you said your u would be cosine squared. Okay, and what would your du be? What's the derivative of cosine squared? So you need the chain rule, right? So the question is that helpful? Well, no, not really, right? You wouldn't do the squared. You'd only do the cosine. So your du is sine x dx, well, negative. So your negative du is equal to sine x dx. So you have that here. Right, substitution, like you need to make sure that when you choose a u, it's not random at all. So what it seems like sometimes like the comments I'm getting here, it's like grasping at straws. Maybe you use the sine, maybe it's the cosine, maybe it's the cosine square. It's not random at all. Like when you pick a u, you're always worried about what is going to happen to my du. Your u needs to be such a thing so that your du is convenient. It's somewhere else in the integral, or you can somehow rewrite your integral easily to get it somewhere else in the integral. The cosine squared isn't going to work because you're going to have a cosine times a sine times the dx, which you don't have. And sure, I guess you can multiply and divide by cosine, but then you get a cosine cubed in the denominator, which messes up everything because you wanted your u to be a cosine squared. So like a cosine squared wouldn't make sense. Like u equals sine also would make sense because your d is going to be cosine and you don't have a cosine in the top. You only had a cosine in the bottom, right? So u equals cosine is going to be the correct substitution. Like it's pretty much the only one here, right? So it's not just a matter of randomly picking. Substitution isn't a matter of randomly picking something to just call u. When you do a substitution, there are really two things you're looking for. One, it's going to make the integral simpler. And two, it's the derivative of that thing is going to be useful, as in I can find it as a factor somewhere else in the integral, or I can rewrite the integral in such a way that I can find it as a factor somewhere in the integral that doesn't actually mess up everything else. So yeah, so if you're doing this integral, one way to do it, it's not the only way. It's probably not the way that I would have done it, but it's doable this way, is to do a substitution u equals cosine. That being said, we can't do that because of the 1, and the earlier suggestion you made in the chat actually fixes that. So the idea was here to break it up into 2 parts. Which is fine. Now the first one is actually just a secant squared, which we know that the antiderivative of that is tangent, so that's fine. Now for the second one is, sure, you could do a substitution, but I would just recognize that that's actually the same as sine over cosine times 1 over cosine, which is just secant tangent. Right, that's a secant times a tangent. And we know that the antiderivative of that is just secant. So that would be the answer. Now, another, you would have gotten this if you did this as a substitution. Like if you did this guy, and do a u equals cosine, your du would be sine, well, be the minus sine dx. And so you see this is literally in your integral right here. That's what makes it a good substitution. If something like that didn't happen, it's the wrong substitution. Think of something else. And so now when you go back, you can plug this in. So this just becomes, where do we go? So this just becomes the integral of 1 over u squared du, which we know is minus 1 over u plus c, which in this case is minus 1 over cosine, because you use cosine. So you just get minus secant. And so this is the part that shows up here. So that would be another way to do an integral. So, and that is, I don't want to say a super common trick, but relatively common. This idea here of when you have trig functions, you have like 1 plus something, you would multiply by 1 minus that thing in order to get a difference of squares idea happening. Or if you had 1 minus something, you could multiply by 1 plus something to get a difference of squares, which happens often. So if we're in another situation, like an integral like, say, cosine x plus sine x, right? Dx, like one trick for an integral like that. And I'm not even guaranteeing that this would work out, but something that you might think about doing is just multiplying by this with the negative sign in between. No, because then you get a cosine squared minus sine squared in the denominator, which you can use sometimes. Or for that to work out, probably if we had like need something else other than a 1 here. But I just want to illustrate the fact that this idea of if you have something plus something multiplying by the same thing with a negative sign in the middle can benefit you if you have like you want a difference of squares situation going on, which with trig identities, that happens pretty often. Because a lot of these trig identities have squares in them. So that would be another way to do this integral. Now, this might looks like something different, But if you actually plug in the trig identities for the tan of x over 2, there are half angle formulas for tangent. You plug it in, you rewrite, simplify, you'll realize you get the same thing. I actually spent a long time on this already, so I don't really want to waste more time talking about that. So here is another example, because I don't want you to get the impression that, yeah, I taught you this whole fancy new technique to deal with this thing, but I could have just dealt with it some other way. Like, do I really need that technique? Well, here's an example where that thing that I just showed you over here on the right is not going to work on this guy, right? Because of the 3 and the 2, right? If we're 1 minus sine x, then I could actually do the same trick that I just showed you, but it's not. It's like a 3 and a 2. It's like, what are you going to do with that? That actually makes it a little bit harder. So it's worth noting here, the trick we did on the above challenge problem won't work. Okay. However, we do have something now called the Weierstrass substitution. So you see something like this, it's a rational trig function. Forget trying to apply any trig identities or cleverly multiplying and dividing by something to get a trig identity to happen, right? Like we did before, it's not going to work here. This one is a little bit more complicated than that. And so a Weierstrass substitution might be a good thing to try here, because it does fit the bill, right? So here we would end up with, okay, so let t equals tangent x over 2. So a couple things happen automatically. I know that my dx, so I know that my dx is going to be equal to 2 over 1 plus t squared dt. And I know that where I see the sine of x, that's going to be 2t over 1 plus t squared. And so now I can actually plug this in. If I call this I, so it's the integral of 1 over 3 minus 2 times sine. So it's 4t over 1 plus t squared times 2 over 1 plus t squared dt. So then I would multiply these guys here. 3 plus 3t squared minus 4t dt. So now the question is, does that actually factor? So we can do some sort of partial fractions thing on it, right? So you would think here, does the denominator factor? So it would have to factor like 3t and t. And the constant term is 3, so it'd have to be like a 3 and a 1. This will give you 9t and 1t. You can't use that to get a 4t, no matter how you distribute the pluses or minuses. So no, it does not factor. All right. So if it does not factor, this means that partial fractions is now off the table. So what can we do if partial fractions is off the table and this is a rational expression? Well, there's a quadratic in the denominator. So completing the square would be something that you would do. And why would you do completing the square? Okay, so do the Weierstrass substitution, we get this guy. Now, myself, if I were a student and I'm seeing this on an exam, now I would think, okay, how do I deal with this guy? So first thing is going to be basic rule, or can I simplify it to be a basic rule? Those two are obviously no. Then I'm going to think, would a substitution work? Well, the only thing worth substituting here is the denominator, but that's an entire quadratic. I would need some t's in the numerator to make that work out. So substitution is not going to work. So then I'm going to think, okay, maybe the denominator factors. Therefore, I can try partial fractions. Turns out that that doesn't work. So now I'm like, okay, so it's not a basic rule. Does it simplify to a basic rule? Substitution is not going to work. The denominator doesn't factor, so I can't do partial fractions. What do I have left? Well, there's trig sub, which actually works with complete squares. So if I can get this to look like a squared minus an x squared, or x squared minus an a squared, or an a squared plus an x squared, that would be useful to me. So what I can do then is I can try to complete the square. Now to complete the square, I know that the coefficient of the squared term needs to be 1, which means I'm going to factor out a 3. And I want to complete the square inside those parentheses. So remember how completing the square works? You add and subtract something. So you add so you add half the coefficient of the linear term. So that's just 2/3, and you square it. And of course, you have to subtract that again because you just added something that wasn't there. Now the first 3 terms become a complete square. They're just going to be t plus the thing inside the parentheses that you added all squared. Now this guy left over here is going to be 4/9. Let me put this in a different color. So that's what that is. So then my entire integral would look something like 3 times t plus 2/3 squared minus 4/9 plus 3 dt. And let's actually expand this out. Minus 4/3 plus 3. Now 3, I can think of that as 9/3, and then I'm subtracting 4/3, so that's just 5/3. Okay, now what I can do is, remember, I want this to look like something that I can use a trig sub on, because none of my other methods are going to work. Trig sub is the last resort. And so I need it to look a variable squared plus a constant squared. So that 3 on the outside of my square here, I'm going to have to move that in. So that's going to look like rad 3. What's the square root of 5/3 squared dt? And so now what we can do is you can do a substitution. And so your du is going to be rad 3 dt. And so 1 over rad 3 du is equal to dt. And so my integral becomes 1 over rad 3 times 2 over u squared plus du. Okay. Now it turns out we have a formula for that. We know that the integral of 1 over x squared plus a squared dx is 1 over a tan inverse x over a. We have that from Rule 19. So this then is going to be one over a. In this case, my a is radical 5 over 3. So 1 over that is radical 3 over 5 times tan inverse of x over a. So that's going to be, in this case, u times rad 3 over rad 5 times 2 from this 2 right here. Plus a constant. So that's just going to be 2 over rad 5 tan inverse of rad 3 over 5 u plus c. But my u is this rad 3 blah blah blah. Okay, and then my t is actually 10 of x over 2. So this is 2 over rad 5 tan inverse of 3 over rad 5 tangent x over 2 plus 2/3. And that's that one. So you can see this is actually a crazy integral. There's no like easy trig integral that would give you an answer like that, where it's like, oh, I can just apply this trig identity. It's like, yeah, and you're gonna get like a tan inverse of a blah 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 tan something plus of a half angle of the, yeah, no, it wouldn't have worked out any nicer way. Like you couldn't do something like this on some guy like that. But with a Weierstrass substitution, you can actually deal with this guy. So that's a long time. So this is an important example because it kind of shows you like when it's a good example of when it would seem like simple enough for a lot of simple techniques to work, but we're forced into a position where we have to use trig sub. And in order to even use that trig sub, you have to do like a completing the square. So it's really one of those guys where it's like, yeah, like the sooner we can get through this on an exam, like really, this is like that problem you put that one problem on an exam to see like who's the A+ student, you know, because you're going to really have to be on top of everything and kind of know how to think. Otherwise, it's going to be really easy to get stuck. But I mean, I am going to tell you exactly how to think, but that's why I'm writing this down so you can know what goes through my head when I'm thinking through a problem. And yeah, so that's that one. So we're going to do a few more examples. 1, 2, 3, 4. Yeah, so we're going to do 4 more examples for this, but we shall do that when we return. Yeah, this is way too long to put on a single thing. So I'll actually leave it like that for now. Take a 5-minute break, and we will come back and finish up the other examples. Okay. All right, let's start. And no one caught me here, but this plus sign should have been a minus sign right here. So when you complete the square, middle sign stays the same, was a minus 4/3. So these pluses should be minuses. Okay, I think that fixes it. All right. So let's get through some other examples to show you around about how to actually go about using Weierstrass to solve problems. And then we will talk about integration in general so that we kind of know, just kind of re-emphasize how we want to think about these problems. Because at this point, I mean, we've only learned a handful of techniques, even though we learned pretty much all the fundamental integration techniques. Anything above this is really icing on the cake. You can go your entire life and never need to know any other technique other than what I'm teaching in this class. And that would be doable for most people. But yeah, even with the few techniques we have, there are so many variations on situations that you can be in that it does take some time and experience to actually know how to actually apply the knowledge that you have. And so I'm going to give you some guidelines on doing that. But until then, for now, let's just actually run through some problems to deal with the Weierstrass substitution. So deal with problems. So when you have a rational expression with trig functions, a rational trig function, Weierstrass can work. So you see something like this here. You go let t equals tan x/2. This implies a bunch of things. So we know that this means our dx would look like 2/1 plus t squared dt. Your sine would look like 2t/1 plus t squared. Tangent, I think it was 2t/1 minus t. T squared, right? So we can actually look at all that and plug that in. So if this is I, our integral would now become one over sine, which is 2t/1 plus t squared, plus tangent 2t/1 minus t squared, times dx, which is 2/1 plus t squared dt, which I think I want this on the other line anyway. Kind of getting too close. All right, so 1 over sine plus tangent dx gives me this guy. Right? And so now we can start to actually multiply out and see what we can actually get here, if this is actually going to be nice. This looks out, it looks very messy so far, but we don't panic before we simplify things. So let's actually get through simplifying things. So be 2 on the top. Obviously, the 1 plus t squared would multiply out, give this 2t, but it doesn't cancel here. So I guess to simplify that, I would multiply by 1 minus t squared over 1 minus t squared. Because we know the trick for simplifying compound fractions is to multiply and divide by the LCD, right? Again, so that's more of a pre-calc thing. So here I have 1 minus t squared over, I would have 2t times 1 minus t squared plus 2t times 1 plus t squared. At this point, I mean, and I guess this was true before as well. 2 is a common term, so just like cancel that out. So this is 1 minus t squared over 2t minus 2t cubed. Oh, no, I got rid of the 2. So it's just t minus t cubed plus t cubed. So the t cubes cancel. So this guy actually isn't that bad. So this is 1 minus t squared divided by 2t. It's so bad compared to the one we just did. So this was just going to be the just going to be the integral of 1 over 2t minus t over 2. So that's going to be 1/2 ln of t minus t squared over 4. And now we can actually replace t with what it is. So this is just going to be 1/2 ln of tangent x over 2 minus tan squared x over 2 over 4. And that's that one. Maybe this would be nicer if I put this. Comma. So that's that problem. You can kind of see it at a glance. So this one, once you clean up the functions a bit, you didn't actually get anything difficult to integrate. Didn't need anything crazy. Didn't even really need a substitution. Just it was a basic rule by the time you simplified everything. So that's nice. So that is doing that problem with the Weierstrass substitution. Any questions on this? Here's another example. Sine x plus cosine x plus 1. Again, that's a rational trig function. So probably Weierstrass, let t equals and t equals tangent x over 2. That means my dx is going to look like 2 over 1 plus t squared dt. My sine x is going to look like 2t over 1 plus t squared. And my cosine x would look like 1 minus t squared over 1 plus t squared. And so now I can actually just plug those in. Sine is 2t over 1 plus t squared. Cosine is 1 minus t squared over 1 plus t squared. Then I have a 1. My dx is 2 over 1 plus t squared dt. I'm just going to, of course, multiply out the 1 plus t squared from the dx part. So this guy is just going to multiply that, multiply that, multiply that. So 1 plus t squared is canceled, just get 2t. 1 minus t squared, be 1 plus t squared. So now let's actually combine like terms. It looks like the t squared is minus t squared plus t squared. So now I just have 1 over 2t plus 2. Get that, which is ln. Which now I can just replace that with the tangent x over 2.
Sorry, I'm going back to the one where you first wrote the I and multiplying it out. Wouldn't you need to multiply the 2 into the numerator?
Right here.
Yeah. Am I missing something?
Yes, so this should be a 2. Which means the 2's cancel here. Which means I don't need the half. Yeah, thank you. So that was a typo. Okay. So something like that. And again, that would be a difficult integral to do from like first principles. In this next integral. So, I mean, here, I gave you a hint because I want you to do something. It's kind of like a Weierstrass substitution, except I don't use the half angle because there's already a double angle present inside the thing. So this was a problem where the hint, I threw the hint in there to kind of let you go through the motions of developing a kind of pseudo Weierstrass triangle, Weierstrass substitution. That being said, if this had shown up on a test, right, I would not do it this way. Like I would have done a similar trick, like multiplying. Let me just say multiply by and put the division in it. 1 minus cosine 2x over 1 minus cosine 2x would be the recommended strategy. It could then be dealt with like the challenge problem. In the first example. But let's follow the hint here. The idea being this will somewhat help you remember how to do a Weierstrass in case you actually forget those equations. You can actually derive them yourself, but it's not as weird with the half angles. This one's a little bit more straightforward. If I use t equals tan x, this of course would mean that your x is tan inverse of t, which means that dx can be replaced by 1 over 1 plus t squared dt. You don't have that multiplication by 2 because I didn't take the half angle. On top of that, also, if t over 1 is equal to tan x, then that means that there's a triangle here where the angle is x. This is opposite over adjacent, so this is going to be 1 plus t squared. And so from this, I can get that my cosine of x is adjacent over hypotenuse. My sine of x is opposite over hypotenuse. And so my cosine of 2x is just going to be cosine squared minus sine squared. So that's just going to be 1 minus t squared over 1 plus t squared. So I can actually just do that and plug them into this guy, right? So this is essentially kind of the there's a route you would go through to actually rederive all those formulas I gave you for the Weierstrass substitution. So if you don't memorize them, notice I didn't box them and put them with green asterisks, which means you don't technically have to memorize them. If you're not going to memorize them, though, you should at least know how to derive them quickly. It just comes down to taking the substitution, solving for x, finding your dx, using the substitution to create a triangle. You can find all your trig functions from that triangle, and you can build up any trig function that you would want. So our integral I in this case is that. So we do have a 1 on top here, 1 plus t squared plus 1 minus t squared. Obviously the t squares die. So this just becomes integral of 1/2 dt, which is t over 2. So that is just tangent x all over 2. Because our t is tangent x here, according to the hint. So a regular Weierstrass substitution would also have worked here. The numbers would be a little bit uglier though. But that is this is nicer because it was already a double angle trig function. So it makes the algebra a little nicer. So finally, this is going to be nice example. So first of all, right, so yes, I know this is a basic rule. We'll figure it out some other way. We'll figure it out. Using a Weierstrass substitution though. So the nice thing about the Weierstrass substitution is it's constructive, and you don't have this random sort of thing happening. So you might remember how we actually derived the integral of, I want to say we did it here. Or maybe we did it here. No. Where did we do that? I forget. Was it lecture 4? I don't know if it's super important that I found this, but there was a point where I actually derived the integral of secant for you. And yeah, it was here. So the idea was you multiplied and divide by this weird thing that actually turned out to be very convenient. It's somewhat reminiscent of that whole, oh, you multiply by, you know, when we had that 1 plus sign in the denominator, you multiply it and divide by 1 minus sign, except that one kind of makes sense because there's a formula in your head, like difference of squares, that you're using it off of, but there's nothing in the denominator of this that would indicate this to you. It's kind of like out of the blue. It's like very weird for someone to come up with that. I mean, this is the standard way to derive this formula, but it's the kind of thing, it's sort of like pulling something out of a hat. And it's like, oh, look at this, it works. You're like, why would you even think of that? But a Weierstrass substitution is not like that. The Weierstrass substitution kind of makes sense from a constructive point of view. Well, let's use an inverse trig function to undo the trig functions to make it something nicer. And you literally can figure out what each trig function would look like and swap them out, right? There's nothing where, oh, something came out of nowhere and we're going to multiply and divide by this random thing. It's a more constructive thing. You can actually figure out what these things are. So if you use a Weierstrass substitution, there's no need to multiply and divide by any mysterious quantities. You can actually directly construct an integral that will help you to figure out the integral of secant. So I thought it'd be really cool to show you guys that. So if I let t equals tangent x over 2, of course we know that this means your dx is going to be 2 over 1 plus t squared dt. We also know that that means the cosine of x is going to be 1 minus t squared over 1 plus t squared. But that means that your secant of x is just going to be 1 plus t squared over 1 minus t squared. Right? And so now you can actually go and you can plug these guys in. We want the integral of secant. But that's actually going to be the integral of secant, which is 1 plus t squared over 1 minus t squared under the Weierstrass substitution times dx, which is that. Your 1 plus t squares would cancel. And you would actually end up with 2 over 1 minus t squared. Right, so now how would you actually do this one? Ideas on this integral. What are you thinking? Give me some ideas here. 2 divided by 1 minus t squared. How would you integrate that?
Is that a partial fraction?
Sure, you could do it with a partial fraction. So that means you've noticed that the denominator can factor. So if we're going to do partial fractions, it has to be those guys. What are the numerators? Start with this one. What's the numerator for that?
1/2.
How'd you get that?
Not sure, kind of blind guess.
Okay, give me a little less of a blind guess. Like what method are you employing here?
Cover-up method.
You can try the cover-up method. Okay, so according to the cover-up method, how would that work? What do you do? If you want to figure out the numerator of 1 minus t, what do you do with the cover-up method?
So for 1 minus t, I think we plug in 2 to 1 plus t. I don't know.
So the cover-up method
But
means
that's
you
not
cover
right.
some. What covers what do we cover up? Just make sure we know all the steps of the cover-up method. Like what do you cover up where?
The
You
one on the
cover
other
up,
side.
sorry.
You go, you go, you go.
You cover up the part of the original denominator that corresponds to the denominator of the arbitrary constant for which you're solving.
Okay, so the original, you're talking about this guy right here, yeah?
Yeah, right.
And we're going to cover up the 1 minus t. And then what do we do?
And then you plug in 1 because that would make 1 minus t 0. So you get
Right.
2 over 2.
So you get 2 over 1 plus 1, right? Which is just 1. Yeah,
Right.
and that's the number up here.
Right.
Right. Okay, so I just want to make sure. So someone said the cover-up method. I don't remember who, but they said you should plug in a 2. I want to make sure, no, you would plug in a 1. And you know what you want to plug in, because remember, you're always plugging in the thing that would make the denominator 0. So t equals 1 would make the denominator 0. So the idea is you go to the original big fraction, you cover up the part of the denominator that corresponds to the denominator that you want to find the top of, and then you plug in what makes that denominator 0. And whatever that calculation gives you is going to be the numerator. And so similarly, you're going to cover this one up. And then you're going to plug in what would make the thing that I just covered up, what would make that 0? Well, if I plug in t equals -1, that would make that 0, right? So then I would actually just plug in 2, 1 minus -1. And I also get a +1. So it turns out that this is a +1 for that. All right, and at that point, now you can do your integration. Technically, you have to do a substitution here. The 1 minus t is u, your du is going to be minus dt. So this is like an ln, but it's going to be a minus ln. This one's going to be a plus ln. And then you plug that in x over 2. And so, yeah, that would be the answer. Now, a reasonable thing to ask is that doesn't look like the answer that we memorized. How do I know that that is even right? And the thing is, does this make sense? I mean, it should make sense. But in that sense, does it match up with the formula we know? Because the formula I had you memorized was this. So question is are these the same? And I guess we can check. So you have minus ln of 1 minus tan x over 2 plus ln 1 plus tan x over 2 plus c. So we know that ln's, when you subtract 2 ln's, it's like ln of the division. Okay, because I wanted to see, I have 2 ln's in this formula and there's 1 ln in the formula that we have memorized. So I'd want to turn it into 1 ln to see if that can help me. And probably what I would do at this point. So there are some half angle formulas for a tangent, but I never remember them because I hardly use them. So I'd probably just write this as sine over cosine. Or use half angle. So here I can multiply by cosine x over 2 and divide by cosine x over 2. Turn this into a simple fraction. Then I guess I can do my trick to kind of compress the denominator here. We're going to do this trick again where we multiply by this guy, but with the sign changed in the middle. The idea being to get that difference of squares thing going. That's going to make this look like a trig identity. So the denominator at this point is going to become cosine squared x over 2 minus sine squared x over 2. I'll write it out. Which we know is the double angle formula for cosine. So the denominator just becomes cosine x in the numerator, I would have essentially cosine squared x over 2 plus 2 sine x over 2 cosine x over 2 plus sine squared x over 2. Now, of course, cosine squared plus sine squared, well, that's just 1. And 2 sine x cosine x is sine of 2x. So this just becomes 1 plus sine x. And so we have 1 over cosine x plus sine x over cosine x. So yeah, it's the same. That's secant, and that's tangent. Yeah, so that's the answer in a different form. But the nice thing about this method is I didn't have to know some mysterious thing to multiply and divide by. I kind of just applied a Weierstrass substitution, which is a legitimate method, and the answer falls out. Now, of course, the answer was given to me in terms of the half angles of a tangent function, but I don't care. It's an antiderivative, and it's equivalent to the other formula that we know, right? This is a bona fide answer right here. So yeah, so we have that. So now, I think we're going to take another break. That's the last example I have for here for the Weierstrass substitution. So that's the last substitution. The last technique. So what I want to do after this, of course, is talk about integration in general. So we've spent about a week now talking about, well, not even, has it been a week? Well, our first couple lectures was just on like hyperbolic trig functions and inverse trig functions. So we spent close to a week in the summer talking about integration techniques, which would be like 3 weeks in the regular semester. But yeah. Yeah, just talking about our integration techniques. And at this point, we've covered all the fundamental techniques I want to show you. And so what I want to do now is talk about just the general approach to integrals, right? So we're going to go back over the art of integration, I called it, because it's kind of an art, not necessarily a science, even though it's not really random. There's a standard way that I want you guys to think about this when approaching different integral problems. So we're going to talk about that after we take another small break. So at this point, we're done with the new integration techniques I want to teach you. It's now just kind of organizing this all in your head, knowing when to use which technique and all that good stuff. That's what we're going to wrap up with. And we might even do, depending on how far we get, play a little integration game, which might be interesting. But we'll see how that goes. So we will take another break now. So go have a drink of water, stretch your legs, and we'll be right back in 5 minutes. All right, so we're back. Let's actually finish up on this. So yeah, let's talk about integration. So this is kind of essentially dealt with in section 7.5 of your text. And we're just going to expand on that a little bit and talk about it. Just general integration strategy, right? Like, how do you approach integrals? As you've probably seen, they're not as straightforward as derivatives. I know I've been saying that, but now you really know I'm telling the truth. So how do you actually go about doing this and knowing, you know, all these, hopefully, of course, it goes without saying that you first need to know the method. So you guys need to go, you need to study step by step how to do each method. But assuming that you know all the methods, you can still be in a situation where you know how to do all these techniques: trig integration, trig substitution, Weierstrass substitution, by parts, partial fractions, but then you still get stuck on a problem because you don't really know when to do which one or what indicates to you when a certain technique needs to be done. So it will be good if we talk about that for a little bit. So that's kind of what I want to do right now. So just how to approach integral computations, the art of integration, right? I call it an art because, like I said, it's not just straightforward. Oh, every time you see this, do that. There's no such thing anymore. There was such a thing when it came to differentiation in Calc 1, integration in Calc 2. Things start getting a little bit more interesting. I want to recap these guys and just talk about how to approach computing integrals, right? So you have this random integral, right? F of x dx, this guy, and that f of x could look like anything, but I want you to ask you to evaluate it, right? What do you actually do? Where do you start? Okay. And we actually already know the first few steps. The first one is to try to apply a basic rule. Basic rules, and this is the one. When I say basic rule, I'm referring to this guy, the chart in lecture 2. Refer to chart in lecture 2. So lecture 2 of our summer 2022 class, there's a chart that gives you all the basic rules. So we have them here. Right. So there are some that I'm not going to require that you memorize, and I already scratched those out. So essentially, they're like, and I added 2 here, like the ln and the secant cube that I would recommend you know as well. But other than that, you should know all these rules essentially. Also, rule 18, probably I don't expect you to know that much, but something like rule 18. It's something that if you see something like that, you can apply a trig sub, and it would actually be an easy trig sub because it will just simplify to 1, and then your integral would just be theta, and it's right away, oh, your x would be a sine theta, so your theta is just going to translate to the sine inverse of x over a. So you could actually do a trig sub on 18 and actually do that, but if you remember it, it'll be a lot nicer. So these are our basic rules. Okay, now when you see an integral, the first thing you think, the first thing you always think, is this a basic rule? Does it look like a basic rule that I know that I can just, oh, it looks like the left side in this chart, and so the answer is going to look like the right side in this chart. Of course, the variable itself doesn't matter. It could be, instead of everywhere you see x's, it could be u's or it could be t's, and it wouldn't matter. The answer, how it looks on, if the problem looks like how it does on the left, then the answer is going to look like how it does on the right. And essentially, like what I was mentioning earlier, every technique that we have is essentially trying to get things to look like this table of basic rules. So either it is in the form of a basic rule or it's not, but you try to make it look like a basic rule. And we have all these techniques to actually get it to look that way. So that is always the first thing you think about. So we're in lecture 7. So the basic rules I'm talking about, if something looks like the integral of 1 over x dx, right? So you know that that's always going to be ln of x plus c, or the integral of x to the n dx, where you know that that's going to be, you add 1 to the power, divide by the new power, as long as your n is not equal to -1, or, the integral of secant squared, and it could be a different variable, say theta d theta. Well, we know that that's going to be tan theta d theta, tan theta plus c, etc. Right? So these are all basic rules, and you can have a sum of them. So you can have like the integral of, 2x cubed minus x to the -1 plus 3 secant x dx. And you know that this is just a bunch of basic rules together, right? So the first one, this one is the power rule, which is this guy. This one is the ln rule, which is that guy. And this guy is just a trig integral that you would have the formula memorized for. So you add 1 to the power, divide by the new power. Here, this just becomes an ln. And here, you know that the antiderivative of secant is just going to be ln of secant x plus 10x and all that plus c. So that's the first situation, right? Which obviously isn't going to happen in Calc 2 very often, right? But if a problem is just a basic rule, it's just given to you as a basic rule, you better figure out that that's what's happening and know how to deal with it. But you do, of course, need to know how to use the basic rules just to be able to finish up a problem, right? When you go through this fancy technique, the whole point of that technique is to get it to look like one of these guys. So you need to know what these guys look like and how to apply them. So this is always the first thing. Is when I'm looking at a basic rule. Now, if it's not, which often it will not be, the next thing you think is, can I simplify it some way in order to be a basic rule? So that's the next thing. So for example, like this guy right here, you know, the integral of this 3x squared minus 2x plus 4 all over x squared, right? It's not a basic rule. However, I can simplify this to look like a basic rule pretty easily. Just divide in the x squared into everybody. And now that's the basic rule for each of those. The first and the third term is the power rule, and the middle term is the ln rule. So that would just become 3x minus 2 ln absolute value of x. Add 1 to the power, divide by the new power. And so that's going to be the answer. So I can simplify this by just like, you know, splitting them up, and we're good at that point, right? And that is just the next level up, right? So if it's not a basic rule, you always look, can I do something algebraically to transform this in a basic, to be a basic rule? Can I like divide into something, right? Now this immediately becomes harder if there's several terms in your denominator, right? So if this was like an x squared plus a 2x plus 5, it's not the same situation anymore. It becomes a lot harder to kind of simplify that. You won't be able to simplify. But in this case, if there's a single term in the denominator, try to divide it into stuff, right? And if there are other things, try to do it. Another one was, which one did we do? Like there was one where I asked you, what is the integral of tangent squared? Right? Which isn't a basic rule. But if you realize, oh, I can simplify that technically and rewrite that in a different way. In fact, I can rewrite this as secant squared minus 1. And those are both basic rules. So the first one, the integral of secant squared, that should be in here. Yeah, that's rule number 8, right? So that one you would know. The integral of tan squared isn't on this list. But this one you would know as a basic rule. And this one is the power rule, right? The integral of 1 is x, not dx, plus c, right? So this is a matter of, this is simplifying. Simplify. Right? Simplify here, I guess, in quotes, right? Simplify just means simplifying really just means writing in a more convenient form, or a form that you can do something with, or it's more compact in some sense. But yeah, this is the second thing you think about. So you see a random integral, the first thing you're going to think, is it a basic rule? If it's not, can I simplify it to look like a basic rule? Can I rewrite it so that I can apply basic rules, right? Now, if those two things don't work, and in a Calc 2 class, it often will be the case that they don't work. The third thing you want to think about is a substitution. Try a substitution, right? And this is the last technique that you learned at the end of Calc 1. But in Calc 2, it's a little bit, it can be a little bit more nuanced. So the thing in Calc 1, all the examples you were given, it's like, okay, if you pick your u, your du is just going to be a factor in the original integrand, you know, barring some constant multiplier. But in Calc 2, The du doesn't have to always be directly visible, but you should be in a scenario where you can tweak it so that it becomes directly visible. Or you tweak it in such a way that you can just swap out the dx and you don't need the du to be directly visible. So here are some 3 examples where it's a little bit more nuanced. So, and the idea behind a substitution is, remember, and this is in general, you always want something to look like a basic rule. That's always the case. So when you see something like this, for example, e to the radical x, right, which is actually an example that we did in class before. You know, the closest thing you have to a rule for that guy is this thing. Now, if you look at that rule, it just says e to the x. There is no radical on the x, and that actually matters, right? So here, when you see this guy, e to the rad x, you're like, well, the rad x is weird. I know how to deal with e to a single variable, not to e to the radical of a variable, right? So it makes sense that if you wanted to do a substitution, the right substitution would be to do something that makes it look closer to a basic rule. So here, the right substitution would be like u equals rad x. Now, of course, if you went in and did du, you're going to see 1 over 2 rad x, which is not visibly present. Technically, you could actually put it in by writing this as like 2 rad x over 2 rad x e to the rad x dx, and that would work. Or you can just rewrite it so you don't need to see it. So for example, you square both sides instead, then your 2u du can replace your dx, and you don't even need to see an extra rad x beside your dx for this thing to work. And so when you plug this in, you end up with the integral of 2u e to the u du, right? Which at this point, you know, by parts is what you would try next, but right? So that one is more doable because it puts you straight into a strategy, but the substitution would be what you would lead with. This one, same thing, right? So you want to get something to look like a basic rule, which means you want it to look simpler in some sense. So you want to get rid of things that make things complicated. Here, the radical in the power of an exponential was complicated. So you use a substitution to get rid of it. Here, having a sum under this radical makes it complicated, because if it were just a single thing under the radical, say like an x squared, you could just simplify that to be x, and then it's not hard anymore. What makes this hard is the fact that there's a sum under the radical. So substitution, you would want to actually get rid of that. So u equals 1 minus x squared would be a good substitution, or even, or better, u squared equals 1 minus x squared. Then your 2u du would be minus 2x dx. And then this guy, you know, is x squared times x dx. So you can actually rewrite it so that your x dx shows up. And so now you know that that's just minus u du. The denominator is u, and your x squared in the numerator, well, that's just, you can use, not there, you can use this to solve for your x squared. And you would see that your x squared is 1 minus u squared. And so now your integral just becomes 1 minus u squared, right? Which is a basic rule. You can actually use the power rule now, right? Same thing for this one. You look at this and you're like, is that a basic rule? No. Can I simplify it to be a basic rule? No. Can a substitution work? Well, if I wanted to do a substitution, what would I substitute? I look for what makes it complicated. What makes it far from a basic rule? The radical, of course, makes it far from a basic rule. So I would want that to be a single variable. So I can do a u equals 1 plus x squared, because the radical of a single variable is nicer, or better, just get rid of radicals altogether do a u squared equals 1 plus x squared. So that substitution would, again, this is 2u du equals 2x dx. This guy I can write as, 1 plus x squared over x squared times x dx, multiply and divide by x. So now I put my dx dx in there. And it actually makes everything better because now I have this x squared as well, which I know what x squared is from this equation. And so my x squared is going to be u squared minus 1. And so my integral would become here u over u squared minus 1 times u du. So this is u squared over u squared minus 1. And now we know how to deal with that. This really became 1 plus 1 over u squared minus 1 by doing that minus 1 plus 1 trick. And I mean, we know how to deal with this. The idea was here to use partial fractions. So you cover up the u minus 1, plug in 1, you get a half. Then you get minus a half when you cover up the other one and plug in minus 1. And so this would end up being u plus 1/2 ln. Right, which you can actually now substitute 1 plus x squared. Right, but the idea is the third thing you think about is substitution. And the idea is also that you want to substitute the thing that makes it complicated. What makes it far from a basic rule? What makes it not simple to actually compute this integral? Replace that with a single variable. Now, of course, you're going to have to play that game. The thing you choose, it's du when you take derivatives, because that's always going to be a part of the substitution. You're eventually going to have to find what the dx is. When you take derivatives, the derivative is also convenient. So this was actually earlier. Yeah, for this one, when we have that the sine over cosine squared, right? U equals cosine makes sense to take. U equals sine x, that would not have worked because your du would be a cosine x. Right? And then you're like, well, maybe I could multiply and divide by cosine to get that to work. But you'd get a cosine cubed here. So you getting that du and forcing it to work, you kind of end up in a situation where what are you going to do with that guy, the cosine cubed in the denominator? You wouldn't be able to go anywhere. And so the u equals cosine was the better substitution to do, right? So you always try the substitution and you pick the thing where it makes things simpler. And by the way, if you're looking at this, and I were to ask you, what makes this complicated? Like, what makes this hard? What makes it farthest away from a basic rule? The denominator would be the answer. It's like a square of a trig function in a denominator. Come on, that's not a basic rule. That's what made it complicated. So you would want to get rid of the denominator with a substitution, right? And, you know, you might have the knee-jerk reaction to take the cosine squared, but obviously by doing the du, you realize that that's going to be a bad idea because you're going to have to do the chain rule in order to differentiate that, and you're going to get, it's going to be worse. Whereas if you just take the cosine without the square, that becomes now convenient. It's right there. The sine of x dx is right there. So your u has to be something that makes things simpler, and at the same time, its derivative is going to be convenient to deal with the remainder. So that's how the substitution works, right? And that's always the third thing. So where are we? So on this test, any test, and for the rest of your integration life, right? The techniques I'm teaching you now are fundamental. Like there will be true in Calc 2, they will be true at every level above Calc 2. At any point from here on after that you're doing an integral, these are the three things you will think first in this order, right? These are the three easiest things to work. And you might go into a discipline where you learn some other techniques and tricks, but even then, these are kind of going to be the first things you think about. And so that's like a substitution. Now, put in red. The above steps, you always take them first. You always take them in this order, right? You are really making your life harder if you don't think that, right? So for you to like see an integral and you just like trig sub, right? Like immediately think trig sub, you're doing yourself a disservice, right? You're gonna make your life impossible or harder for no reason. Think of the low-hanging fruit first. Is it a basic rule? Can I simplify it to be a basic rule? Can a substitution work? In the event that any of these things work, it'll be much easier than trying to apply anything else. So yeah, you think of these things first. It's also pretty quick. You can get instant feedback as to whether the method is going right for you, because if your substitution isn't working, you won't be able to plug things into the integral. Like you get stopped right away on the first level, right? So it's not like you're gonna start working stuff out and then figure out like 10 minutes later, oh man, I shouldn't have done a substitution. No, if your substitution wasn't gonna work, you're gonna find out on the first line that it's not gonna work, right? And so if you know that, now you know, all right, let me just go something else, like a substitution isn't going to work here, right? Like when I had this integral of 1/1 plus sine x, can a substitution work? Well, u equals 1 plus sine x is literally the only thing that would make sense in a substitution. Maybe even a u equals sine. But the moment I go du, cosine, up. There's no way I can force a cosine into this thing without messing things up. Because if I put a cosine up here, I'm going to have to put one down here. And what is that cosine going to be? Well, plus or minus 1 minus sine. Like, what am I doing to myself? Like, it's not going to work, right? Like, if a substitution doesn't work, you're going to know right away that it doesn't work. So it's not like you're going to waste time checking. Always check if a substitution would work, right? Because in this example, for instance, like a substitution first would be the way to do it, but it's not obvious right away that a substitution would work. So try it anyway. See if you can finagle things to get a substitution to work, because if you can, you're almost home free. Sure, you can end up with something where you would need another technique, as you do here. This runs into integration by parts, but with a substitution, it'll always be easier to see what's going on. Like with a e to the radical x, you don't know what to do with that, but this guy is kind of more obvious to do integration by parts. Speaking of which, that's the next technique we looked at, integration by parts. So as I mentioned, the above three things, you always do them in that order. Everything after this point is not in order. So I put the number in quotations because sure, I call this step 4, but it's not really 4. It's not always the 4th thing you think about, right? It's just the 4th technique you learned, right? So I numbered the rest in the order in which I introduced them to you in the class, but they don't come in order. So integration by parts is another technique, and it's not necessarily in order. But a 4th thing that you could think about, 4 being quotations, is integration by parts. Now, you might want to know, when can I do integration by parts? Well, there are a few situations. One is you have a product of 2 different types of functions. That would be an indicator that you have to use integration by parts. So, for example, e to the x times sine x, or x cubed times e to the x. Here you have an exponential times a trig function, or polynomial times an exponential function, or you're going to have a polynomial times a logarithm, or you have 2 different kinds of functions and you're multiplying them together, right? Now, I would point out that a non-example would be this one. So if I see this, if I see this integral, yes, it is a polynomial times a trig function, right? But it is not something that I would do integration by parts for. Why? Because it's actually a substitution problem. Like for this, I would do u equals x to the fourth. Du would be 4x cubed dx. So then this integral is just a quarter times sine u. So that's just going to be minus a quarter cosine u plus c. Right? So again, it's a substitution problem. But I'm assuming that if you make it to this level, you would have already checked that a substitution wouldn't work. Now here, the fact that you have a sine with an x to the fourth in the angle is very weird, right? Like sine x dx, basic rule. You go sine x squared. This is now an impossible integral. And I don't mean it's difficult to do. I literally mean it's impossible. Like you cannot write down in terms of any elementary functions what this integral is, right? There's no function you can think of that if you took the derivative according to regular derivative rules, it will give you sine of x squared as the answer. So yeah, sine of x to the n when your n is bigger than 1 is automatically something that you think as suspicious. That's suspect, right? Like I can't do that. So if I saw this integral, I would not think integration by parts. I would have already thought about substitution, and the prime candidate for what to substitute would have been the x to the fourth, because sine of x to the 1 is easy. Sine of x to some higher power is hard. I would get rid of the variable to the higher power, right? So this is a non-example, right? But assuming that you're following the strategy, you would have recognized that. But these two are not such cases, right? So here, integration by parts would be how we would apply this one. And for this one, you would also probably want to employ the tabular method, right? Which is streamlining the integration by parts. Another situation is when you have one function, but it would be more convenient to have the derivative of that function than it would be to have the function itself. Or finding a derivative of a part of the function would be useful, as is the case with the secant cube. So here, the tan inverse is not nice. However, the derivative of tan inverse, ddx of tan inverse, is something that's nicer. 1 over 1 plus x squared. So this guy here, it seems more manageable. Right? So if I'm in a situation where it's not a product of two functions, however, it is just one function on its own, but it would be nicer to have the derivative of that function in play, then integration by parts would be nice, because you would just say u equals that function, your dv would be 1 dx. Right, so we did that. So it would be nice to just go u equals tan inverse, and dv would be your dx. Your du is going to be that 1 over 1 plus x squared. Your v is going to be x. And so your I is just u times v minus the integral of v du. And now you realize that this guy is substitution. Now, every time, by the way, you restart art of integration, with every new integral. So we started off with this integral. We applied a technique to get this integral. Once you get there, just because you started off with integration by parts doesn't mean you're stuck with integration by parts forever, right? You can apply another technique at some point, right? Every time you see a new integral pop up, you start from the beginning. Is this a basic rule? Can I simplify it to be a basic rule? Would a substitution work? And here, clearly, 1 plus x squared would be a nice substitution. Your du would be 2x dx. And so you can actually get that, you have that x dx in the numerator, right? Secant squared, we saw that one. That was a kind of a weird example, but the trick was to actually write it as the product. And you know that the integral of this is nice. And the derivative of this is nice. So choosing this to be your u and choosing this to be your dv would be actually a nice thing to actually try. Okay, so integration by parts is another technique. It's not necessarily the fourth thing you think about, but if you're thinking about integration by parts, there are two scenarios in which this is convenient, right? So you either want to have a product of two different functions, or you have one function where either its derivative or if I have a derivative of a part of it, it would be very convenient to have. Okay. Now, there are times when it might seem like a technique like this would work, but it won't work. So for this one, it's this is impossible. No general antiderivative. So no technique that we've learned in class is going to do this one, because that one can't really be done. This one, though, if you have the two trig functions multiplying by each other, this is going to be, it's actually would lead int by parts. If you try int by parts, you would actually end up with like a 0 = 0 situation, like both sides of your equation would cancel. But the trick here is for something like this is product to sum formulas. Is the way you would actually do that one, which I think I actually pasted that somewhere. So if you apply like the sine times the cosine, apply this formula, that actually would make this easier to deal with. So you have like these weird situations, although I'm not going to ask something where you would need to know a product to sum formula, but just to know, things can get crazy with integrals. Like there are a bunch of integrals that are impossible to do. So, but the ones that you'd see in Calc 2 are these kinds. And this is when you would want to try an integration by parts. And again, just to reemphasize, everything I talk about from this point on, I am assuming that you've already tried to apply a basic rule, tried to simplify it to apply a basic rule, or tried a substitution. And I'm assuming that those did not work. You do not think about anything from this point on before trying those previous three things. Okay, so I'm just going to assume that we've already tried all that other stuff. So we learned a fifth thing, and this was just trig integrals, essentially. And this is just when you have trig functions, right? So integrals like sine over the radical of 1 plus cosine, or, you know, sine to some power times cosine to some power, or secant to some power times tangent to some power, or even this other one, right? So the main idea here is, if you notice that applying some trig identities could be useful, or if you do or isolating something so a substitution could take effect that makes a trig identity useful, is the idea here. I think the trig integrals were more straightforward in some sense in knowing when they can apply. It's just that, and that's easy to identify. It's when you literally have a function of trig functions, right? Like you can see the trig in it, then you would apply these techniques. So this is from like section 7.2, I think. I want to say. Yes. But that's all a matter of applying trig identities or using like a substitution to get to a trig identity. Now, another technique would be trig substitution. Now, again, I am assuming you tried regular substitution and it did not work. Do not think trig substitution before you think regular substitution, right? You do not think almost anything beyond integration by parts if you haven't already thought of a regular substitution, okay? So assuming that you do not have a regular substitution did not work, and this is also very important, you do not have trig functions to begin with. Something where trig substitution can work on, there can be no trig functions in the first place. Trig substitution introduces trig functions in a situation where there were none before, right? So if there is a trig function in your integral, trig sub cannot work on any of these because there are already trig functions. Trig substitution works when there are not trig functions. However, you have expressions like this, or this, or this. And those allow you to take advantage of trig identities, right? So I would say things to note here, make sure a regular substitution does not work, right? And I would also say, if you're using this on a definite integral, always change the limits. Don't go through that whole drawing the triangle for the back substitution thing. You'd be wasting a lot of time. Also understand that the forms above can be flexible. Your x can be anything. So for example, in this case, like this is something where you could do a trig sub on, where you just think of your x as the 3x plus 1, and your a would be square root of 5, right? So just, you don't have to have, these don't have to be nice integers or anything like that for this to work. You can think of a as, you can think of any like number as the radical of that number squared, and you can apply a trig substitution in the event that it's actually useful. Okay, so that's where a trig substitution work. You do not have trig functions to start with. You would generally have something with some polynomial type component. Maybe there would be some radicals in it or something like that. And a regular substitution would not work. And I spoke about how to tell when a trig sub versus a regular sub would work versus not work. We did that when you look at the odd power, right? So trig, when to use a trig sub versus a regular sub, when to know one would work versus the other, right? There's a very nice eyeball test between the power of x, whether it's odd or even elsewhere in the function. Okay, so yeah, so assuming that you don't have trig functions to begin with, one of these three situations is true, and assuming that you can actually, you've actually already tried a regular substitution, a trig sub might be the way to go. Okay, and I would say generally you kind of want to use trig sub as a last resort. There are some times where a trig sub could technically work, but I'd rather use a partial fractions application. But the partial fractions is a little bit more restrictive. So I might also say, also check partial fractions won't work. Which for partial fractions, it's also going to be obvious when that won't work. Like you're going to know right away when a partial fractions won't work. In fact, that's the next thing we want to talk about. So when does a partial fractions work? One, the integrand is a rational function, ratio of polynomials. So I mean rational function in the strict sense. Or possibly you could do a substitution that makes it into such a function. But again, I'm assuming that you've already tried a substitution, so I'm not going to talk about that case. So it's a rational function where the denominator factors, and it is a proper rational function. We've already seen how to deal with a situation where it isn't. Okay, and let me even remind you again, you only think about this step if steps 1 through 3 won't work, right? And in the case, the thing to note, the function must be proper. If it's not proper, you can actually make it proper by doing like those the tricks here. So this one, try to get the denominator in the top, so I would subtract 1, add 1. And so this one here is now proper. So partial fractions can work. Okay. So for this one, again, I could just add 1 and subtract 1. So that'll be 1 minus 1 over x squared plus 1. This one you don't even need partial fractions, so that would actually just be tan inverse. So, but the idea is sometimes you make something proper and you realize that, hey, I don't even need, like you might think, oh, a partial fraction is going to work here, but after actually putting it in the form where you can use the partial fractions, you realize you don't even need the partial fractions. Okay, so that's the scenario. Lastly, what we did today, the Weierstrass substitution. Okay, so this is when you have a rational function of trig functions. So that basically means, looks like a ratio of polynomials, but the variables are replaced with trig functions. Okay, so the two examples I have here are such examples. Now, the thing I would caution you here is to actually make sure that like a regular trig identity won't help. So for this one, did I actually beat that? Didn't make that note. So I would of course check that the methods of 7.2 or trig identities won't help. So for this one, we actually did an example of this earlier, where a nice trick was just to multiply by this. And we realized that that eventually became just the integral of secant squared. I think it was plus secant tangent. Okay. So here trig identities help. Trig IDs help. So would not use Weierstrass. Unless you didn't notice that, then you should. Unless you didn't notice. Which is another thing. Many of the problems here, there will be several techniques that would work, but you some would be easier than the others. So you always try to get the easier one to work first. This one here, trig identities won't work. And that was all the techniques. So again, there is no specific order to go through with them, but you always try these three things first in this order. Is it a basic rule? Can I simplify it to look like a basic rule? Can a substitution work? You always try these things first. Now, you might be in a situation where they don't work. Now, if you find that the situation you're in is that you have a product of two different kinds of functions, or you have a single function where it would be nicer to, if that were the derivative of the function, then by parts might be something that can work. If you have just a function of trig functions, then obviously you start thinking about trig integrals and applying the methods of what we learned in 7.2, right? So either like a u equals sine or u equals cosine or whatever to get the substitution to work out, or doing, and you know, if the powers are odd or even, there's a whole bunch of things there. So that should be like, if you see trig integrals, you should start thinking about the methods that we learned in 7.2, right? We learned a few of them. Now, another thing is trig substitution. And I would say it should be one of the last things you should think about. Like, you really only do this when you kind of have no other choice, but it's important that you don't have trig functions in the beginning. You only have like algebraic expressions. You can have radicals in them, that's fine, but you need to have an expression like x squared minus a squared, x squared plus a squared minus x squared. If you don't have that, you cannot use trig sub. Partial fractions. This only works on rational functions, so ratios of polynomials, where the highest power on top is strictly smaller than the highest power on the bottom, and the denominator factors. So either you have that situation, or you can get to that situation with a substitution. And that would mean a partial fractions can work. And the Weierstrass substitution, you're in a situation where you have a rational function made up of trig functions, and trig identities or the methods of 7.2 don't work. Then you can do a Weierstrass substitution. And so it's not necessarily things you think in order, you just look at the situation you're in and say, what would be the appropriate method here? Oh, it's a rational function, the denominator factors, the highest power is on the bottom. Partial fractions is the thing that you should try, right? Assuming that a substitution wouldn't work. Okay, and that's basically it. Now, I actually wanted to talk about one more integral that someone was asked me about, so I thought I would talk about this. Now, there was an exercise I wanted to do with this guy here. I guess we can do it at the beginning of next week. So we'll do this next week. But yeah, I mean, in terms of like the method and when we apply any methods, are there any questions on that? Yeah, I won't require that you know this. I just wanted to point out that there can be some weird situations. And it really depends on what you covered in your pre-calc class. Like when I teach pre-calc, I don't really talk about those formulas. But they're actually pretty useful and they come up often. Like there are times, like I have to talk about that formula when I'm teaching differential equations, for example. Yeah. But this was a problem that someone asked me about, so I thought I would actually just it might be nice for benefit, because it's one of those where you use a combination of techniques because you know it's almost good enough for some technique to work, but not quite good enough, so you kind of mix and match. And so the thing is here, so here's what I would want to try. Because it's not a basic rule, can't really simplify to be a basic rule because there are too many things in the denominator. So I would want to do like a U sub. but then my du is going to be 2x plus 1 dx. Or in other words, if I factor off the 2 because there's only an x, be x plus a half dx. So the thing is, I don't really have what I need for a substitution. I do have the x, but that minus 2 is in the way. So here's something that you could actually try to get to work. You could actually just break this up into 2 parts. Put the x plus 1/2. And then, so I'm going to write the minus 2 in a way that I can have 1/2 there as well. And so that's going to be minus 5/2. If you take plus a half minus 5/2, you actually get minus 2 as the answer. So I can actually break this into 2 parts. So with the first one, a substitution would work, but not with the second one. So I would break this up. Say 5/2. Okay, now for this one, a substitution is going to work. So that's going to lead to 1/2 ln of x squared plus x plus 1. Now for this one, if we focus on that. So all right, we got rid of the part that a substitution could help us with. Now we're left over with this part. What do we do? So now you check, does the denominator factor? And no, denominator does not factor. So, which means partial fractions won't work. And we know that substitution won't work. I, in fact, used up all the substitution that I could use up already is already used, right? Like this is the part that substitution didn't work on. So substitution is not going to work. Partial fraction is not going to work. But I have a ratio of polynomials. Integration by parts, like how I don't have a product of 2 different kinds of functions. And I don't see how the derivative of this function will make things easier, because I take the derivative of this and I have to use the chain rule. It's actually going to end up worse. So at this point is where I'm like, okay, I should try a trig sub, in which case I would need to complete the square. So that leaves me with 5/2 times integral of, this will be x plus a half squared, because it's, okay, then when I square that, I would get a quarter, and I want that to add up to 1, so it'd have to be 3/4 over here. And then this is almost like a basic rule, but you probably won't see it without another substitution at this point. U equals x plus a half. You'll notice that this looks like minus 5/2 like that. And in fact, the 3/4, you can think of this as radical 3/2 all squared. And at this point, there's a basic rule for that. It's the 1/u squared plus a squared. We know that's 1/a tan inverse x over a. So I actually used this trick earlier. So this actually becomes minus 5/2 times 1 over a tan inverse x over a. And then I can just replace my u with what the x is supposed to be. So this just becomes u was x plus a half. So that would be that integral. Right, but it's another one where you can mix and match these techniques. Sometimes you have to split an integral in two, and a nice technique will work on one half, the other half is kind of annoying, but yeah, essentially that's it. So that's the art of integration. That's kind of us filling out that table and how you want to think about things. And I left off with another relatively challenging example. But yeah, we will stop there. So we've done integration techniques. Next week, we're gonna do some more integration, but it's more like integration in a special situation. So you won't need to know any new techniques other than what we've already seen. But yeah, we will stop here for now. So long weekend, look over your integration techniques, practice a bunch of problems, especially if you're kind of struggling with integration, which I mean, it's the summer, so we've been moving pretty quickly. You don't want to go into next week kind of being shaky on this, so really hunker down this weekend, get some practice in, and I will see you guys on Monday, where we're actually gonna play a little game to start off, get the brain juices flowing, and then we will talk about improper integrals, I think is the next topic, as well as numerical integration, which numerical integration shouldn't be a big deal. Improper integrals, there's a little bit of concepts that I need to teach you first, but we will end there for now. Unless there are any questions before we leave. Well, if questions come up, you guys can email me or ask me in next class, I guess, if it's not super urgent, but we're going to end right there. So have a good night. Enjoy your weekend. I'll see you guys in the next one. Ciao.